So let's continue. Yesterday we stopped here. It's about the simultaneity and time dilation. Actually, so we know that suppose this B does not move relative to the mirror, and the distance between this B and the mirror is D. So in this case, the light moves for a distance 2D, and it measures the time to be delta t0, delta t0. So actually, the speed of light should be c. So which means that 2d over delta t0 should be c. And in this case, suppose this is a b moving with a velocity v, which is actually parallel to the mirror. And in this case, suppose this v is quite fast relative to the speed of light. And in this case, it emits the light going this way for a distance L, for displacement L. So actually 2L when it go to the mirror and then go back. So in this case, suppose you have a clock. You have a clock here, and you have another clock here. And then suppose a guy is waiting there, a guy A there, a guy B there, reading the clock. Suppose these two clocks is synchronized, and it read the time, and read the time here. So A and B will see the delta t, the time difference will be delta t rather than delta t0. Delta t0. So actually there are two clock there. Actually the clock doesn't move. And actually it will feel like the time is delayed. 时间膨胀了。那实际上actually if there is someone on this B, maybe I put it C here. Maybe I put it C here. Maybe I put this one is C. Maybe this one is C. So actually B will see the light maybe actually at that time here. So B move to this point and the light move to this point. So relative to B, actually it see the lights moving the distance this way. And suppose B move to this point. You see the lights moving to that way. So relative to B, actually you see the lights like this guy. It doesn't feel like the light has moved for a part of L. Doesn't like that way. Actually, it feels like the light moving upward, barely upward. So actually for B, it will feel like it only pass for delta t0. But if you have two clocks, one is at this point, this clock is at this point. If A and C, A read the clock 1, C reads the clock 2, then this time difference will be delta t rather than delta t0. And delta t0 is called the proper time. So in this case, we can do some calculation. We know that this is a right angle triangle. 是一个直角三角形嘛。那直角三角形so actually for right angle triangle, it should satisfy the Pythagorean theorem. Pythagorean theorem 就是毕氏定理嘛，或者叫高古定理嘛。那就是 L 平方加L square plus D square. No, not plus. L square is the L squared equals D squared plus total is V delta T. So 1/2 is V delta T over 2. So only satisfy this simple equation. And we know that L is C delta T over 2. C delta T over 2 squared equals this one. We have D equals to C delta T0, C delta T0 over 2 plus V delta T over 2 squared. So in this case, 2 can be cancelled. C and then it feel like, so you can just move this term to the left side. So we have C squared minus V squared multiplied by delta T squared equals to C squared delta T0 squared, right? So actually we can just move this guy to the right side, and take the square root on both sides. So finally we have a delta T to be delta T0 over C squared over V squared over C squared, and then take the square roots, right? Because C squared is in the denominator, so we just put it here, and then we take the square root. It will feel like delta T0, take the square root. C squared over C squared is 1 minus V over C squared. So we will have come up with this equation 37.7. And we will also define B to be this ratio between the speed and the speed of light. So this is called the beta, and another factor called the gamma, which is 1 over square root of 1 minus beta square. And this is called the Lorentz factor. So actually this factor appear quite a lot in the special relativity. And yeah, it's something similar to this. So you can imagine if V is very small, very small, much smaller than the speed of light, which means that a beta equals to V over C would be close to zero. So it feels like nothing because we have 1 over 0 and then take the square root. So this term disappeared. So for normal life, we actually don't move quite fast relative to the speed of light. So we didn't feel this effect in the past. But something like 120 years ago or 115 years ago, so Einstein made this kind of thought experiment. 它叫做思想实验啊。那爱因斯坦可以用思想做实验，那我们是反复数值啊，我们要去实验室做实验。Okay, so he only make use of the simple geometry and some crazy idea. So he come up with this result. And actually, a light source and mirror Yeah. So any question regarding to this one? Okay, so yeah, it's just some simple. Yeah, it's just a simple derivation. I just let you know. So it's just actually the same as what I wrote just now. So there's a sample problem. So here we have okay. Okay. So your starship passes Earth with a relative speed of 0.999 c, 0.999 c. So very close to the speed of light. Because if we just move in a normal speed like in a rocket, it's already quite fast. Maybe hundreds of not hundreds. Yeah, maybe just a few kilometers per second is already quite fast. But when you're talking about the interstellar travel, then it's not really possible. So assume your starship passed the Earth with a speed of 0.999 c. After traveling 10 year, you stop at lookout post LP13, turn and then travel back to Earth with the same relative speed. The trip back take another 10 years. Yeah, because suppose the distance doesn't change and you use the same velocity, same speed to go back, your time. So how long does the round trip take according to the measurement on Earth? Neglect any effect due to the acceleration involved with stopping, turning, and getting back up to speed. 所以这个是一个很有名的叫做 Twin Paradox 双生子悖论啊。那这个悖论就是需要用那个广义相对论才能解释的啊，所以他在这里的时候他说 neglect any effect due to the acceleration involved with the stopping, turning, and getting back to the speed. But so it doesn't, so it makes it like a paradox, 像一个悖论啊，但是这个就是有趣的地方。So actually calculating the answer to this one is quite easy. You just need to plug in. Delta t equals delta t0 square root 1 minus v over c square. So you just need to make use of this simple equation. So 10 years is your time, which means the proper time. You only have one clock. So delta t is 10 year, and then square root 1 minus 0.9990 over c. So c and c cancelled, so it becomes 0.999 square, and 1 minus this one, and then take the square root. So it becomes 223.7 year. So delta t for the round trip, round trip 就是来回嘛 ，round trip， 那就是so this should be 2 times delta t, which is 447.4 year. So this is the answer. So actually, if you are on this starship, you only pass for 20 years. So 2 times delta T0 is actually 20 years. But on the Earth, it already passed for 447 years. Maybe you can just slightly adjust the maybe the time. Maybe you make this one smaller, or maybe you can make this speed smaller. So it feels like suppose for this twin paradox, it's talk about suppose there are 2 twins, maybe they are a kid. One is on the starship and go to somewhere with a very high velocity and then go back, and then feel like, oh, one of the twins still maybe 10 years later, maybe 5 years later, or it's only maybe just like an 10-year-old, but the other one already an old guy. 所以这个是双生子阳谋中文的话就是有2个很小的双生子，就是 twins 嘛。那其中一个上了一个太空船用一个很高的速度离开地球，走了比如说5年，然后用5年回来那回来的时候就发现那个坐了太空船出去再回来之后他可能只是过了10年。但是另外一个留在地球的他回来之后就已经很老了所以这个是双生子阳谬。那这个或者是悖论，那这个悖论所在的意义是一个人朝着地球离去那反过来说他离去你也可以看作是那个地球离那个太空船以一个反方向的速度离开。所以这个悖论的那个点是在哪里？它就是在那里，就是说只用狭义相对论的话，你没有办法解释说为什么是坐在太空船的那个人没有那么老，留在地球的那个人呢就变老了很多那这个需要用广义相对论才能解释，但是我不会了我不会。So here's another sample problem. So the elementary particle known as the positive kaon is unstable in that it can decay, transform into other particle. Although the decay occurs randomly, we find that on average a positive kaon has a lifetime of 0.1237 millisecond when stationary. That is, when stationary, which means for the proper time. So that is when the lifetime is measured in the rest frame of the kaon. If a positive kaon has a speed of 0.99 c relative to the lab reference frame, when the kaon is produced, how far can it travel in that frame during its lifetime according to classic physics, which is a reasonable approximation of speed much less than c, and according to the special relativity, which is correct for the physical possible speed. So first one, according to the classical physics, 根据古典物理的话so it's only v times delta t, so which is nothing but v is 0.9990 c. Maybe I can just write it out. C is 2.998 times 10 to 8 meter per second. So this is the v, and delta t delta t is 0.1237 times 10 to minus 6 second. So it is like 36.7 meter. 36.7 meter. So according to the special relativity, so V delta t should be V delta t 0 over 1 minus V over C quantity square root. So so in this case, it should be like 0.990 times 2.998 times 10 to 8, and then times 0.1237 times 10 to minus 6. So actually the this one is actually this one. And then for the denominator, it is 1 minus 0.990 C over C, and then square. Take the square root. So it feels like it moves for 258.7 meter. 0.7 meter. So this is for classical physics. This answer consider the special relativity effect. So any questions? So next we talk about the relativity of the length. So actually in the past we will consider, suppose we have S equals Vt. At that time we will consider T should be absolute. 时间是绝对的，我们会想说，那时间是绝对的情况之下，我们就会有过去的那种计算那个 v 就会相加嘛，就是比如说我们相对而行的话，那速度就会相加。那但是我们发现光速是绝对的，现在的情况是光速是绝对的，所以现在有那个c 等于l delta t。那现在是光速是绝对的，那时间就不是绝对的，时间不是绝对的话，那长度也要跟着变，So in this case, if the relative speed between the frame is v, the contract length L and the proper length L are related by this equation. So if you like at that time in the previous slide, we know that delta t is delta t 0 times gamma, and so times gamma. So now L should be the L0 divided by gamma rather than that. So in that case, suppose L0 and delta t0 should be equals to L delta t, something like that. It's just like you measure the length by the speed of light and the time. So the time is delayed, and in the other way, the length should be contract. So it asks, does the moving object really shrink? 就是缩小了啊。So reality is based on observation and measurements. If the results are always consistent and if no error can be determined, then what is observed and measured is real. In that sense, the object really does shrink. However, a more precise statement is that the object is really measured to shrink motion effect, that measurement, that and thus reality. Oh. Okay. So let's see a sample problem. So you may have more idea about this one. So here we have a Sally at point A, and Sam's spaceship pass Sally. Sally is stationary there, stop here there, and then Sam's spaceship of proper length, which means that if it does not move and we try to measure the length of this spaceship, it is 230 meters. So pass each other with constant relative speed v. So it moves at speed v. So you try to measure, Sally try to measure the length of this spaceship. So pass each other. So Sally measured the time interval of 3.57 milliseconds. So at this point, start the stopwatch, and then when the ship pass at point C, so it stop the stopwatch, and then this delta t is 3.57 millisecond, 3.57 millisecond, and actually the relative speed can be measured accurately because you know that they share the same relative speed of v. So in terms of C, what is the relative? It asks you what is the relative speed v between Sally and the ship. So in this case, we have v equals to L over delta t, which is actually L0 over gamma, because actually this one is moving relative to Sally. So Sally will see the length, will have the length contraction. And this is actually delta t. So in this case, we have L0 multiplied by 1 minus V over C squared over delta t. So we can multiply this one to the left side, divide this one on both sides. So we have V delta t over L0, and then take the square on both sides, which will become 1 minus V squared over C squared. So we can move this one to the left side and then factor the V squared out. So we have V squared delta T over L0 square plus 1 equals 1. So V would be delta T over L0 square plus 1 minus 1/2 power. Not this one. So here we should have 1 over C squared. 1 over C squared should be like this. So we can just add them together. We have L0 squared C squared, and then C squared delta T squared plus L0 squared, and then take the negative 1/2 power. So it will becomes L0C over square roots of C delta T square plus L0 square. So we substitute everything in it, and we will have L0 is 230 meter, and then so in terms of C, so we don't need to plug in 2.998 times 10 to the 8th power, and then this one. This one is 3.57 3.57 times 10 to minus 6, and then times 2.998 times 10 to the 8th, and then take the square, which plus L0 square. L0 square is 230 square. So if you like it is 0.210 C. 0.210 C. Actually, if you just plug in delta T 0 there, maybe you can just calculate it by V equals L over delta T. Delta T to be 3.57. So you feel like 230 divided by 3.57 times 10 to minus 6. So let me check. So you feel like 230 divided by 3.57. So it will become, so this one will become, let me see, 6.4 times 10 to the 7 meter per second, which is actually 2.998 exp8. So you feel like it is actually 0.215 C, which is quite similar to this one, because if you consider the factor, the gamma factor, the Lorentz factor, which is 1 minus V over C square, take the square root. This term, suppose you plug in 0.210 square. This term is still 0.978, which is quite close to 1. So it doesn't feel like there are much error. But as long as the speeds increase further, or if you need a higher precision, then you need to consider the special relativity effect. Actually, for the GPS, you need to consider the special relativity effect to make the estimation of the position to be much accurate. Okay, so maybe we just stop here.